For the last portion of Chapter 6, we need to go over a couple of inbuilt functions in MATLAB that make a lot of this process we've been discussing throughout very easy. The first one is polyfit. You know, pull up the help file here, or you can go online and, of course, use the nicer help file that's available for the function, either online or through the MATLAB help documentation. But this gives you the basics. Basically, polyfit is one function that can do more or less any degree of polynomial fit for a set of data x and y, which I conveniently have already entered in from the textbook example. The data there stored on page 237. So what we are going to do is use polyfit to generate the coefficients C of this x and y data of various orders. Let's start with a first order polyfit line. So that would be a straight line with coefficient 1, 7.03, coefficient 2, negative 4.9493. So let's actually plot that. If we did a plot of x, y, the data looks like that. It's not continuous yet. We should actually just represent this accurately with a plus, so that way the data points show up as just little individual marks. If we go in and use our coefficients we've learned of to make another plot, same x values. For the y values, we will be doing an output generation. So we would take every value x times 7.0393, which is our coefficient. We can actually just call that c of 1 plus c of 2. I think that'll work. Did it work? Hey, it did. So that is our linear best fit for that line. In fact, I'm going to do one better and turn the command hold on, so that puts a hold on the plot we are making so that when we do new plots, it'll just right over the top. So this should allow us to show various curve fits. So say now C is polyfit. Sounds like some sort of denture cream. We can do 2. That generates the second order coefficients for the best fit of the data provided in x and y. So in this case, we would go back to our plot command and see if I can't screw this up horribly. X dot squared times c, actually be c1, then the indices move down, c2, c3. Is that right? We will see. Should be. Hey, it is. That actually looks about right. So that's the second order best fit going through that data. And you see how this is going. We can just continue on by generating, let's skip straight to the fourth order, because why not? Let's go back to our plot and we'll have to add a couple of new coefficients. X dot to the fourth times C1 plus X dot to the third times C2. Modify these other coefficients. 3, 4, 5. Yeah, sure, why not? Let's see how bad it goes. Hey, not terribly. Okay, so let's make this big and talk about it. Data points, all the green pluses. First order fit, this orange straight line, not a very good fit at all. Second order fit, purple curve, you see it's just, it's sloped up, it's increasing, it's a quadratic equation. Fourth order fit's actually starting to fit this data very nicely. It curves just as along with the data. The data doesn't appear noisy, it just appears to have a natural shape. So that's a nice fit. But this shows that you can very quickly determine all of the coefficients for a polynomial that you need, and in fact each one of those coefficients is stored at machine precision. I just need to change my display back, and so if we did polyfit to the fourth, you see it is actually quite a large amount of precision stored in memory for each one of those coefficients, making it a very accurate process. It is best to generate these coefficients in the software you are going to use it in. So if you're going to be doing curve fitting or regression of data, do it in the same piece of software so you're not left writing these down on a napkin and translating them to Excel or carrying them across campus, and who knows what you're doing with it. But you do not want to lose significant figures in these leading coefficients as you're transferring this to other areas in a research project.